I want to give a warm welcome back once again to David.
Yeah. How many people were here last week or the last month meeting? For those of you who are not at the last meeting, I apologize in advance for what's going to happen here. So I've been trying to understand Python a little bit better. It's kind of been an ongoing process. The talk I gave at the last meeting was kind of like a snapshot in time of sort of what I had figured out at that moment. Still trying to kind of wrap my brain around what's going on, how the PyPy project works. So this is kind of a second installment of that. We're going to look at something a little bit different, just as a little bit of a recap, in case you were not at the last meeting. That's the PyPy project, which has been getting a lot of buzz because they have this version of Python that runs a lot faster than normal Python. And one of the things that's kind of unusual about that project is that it's essentially an implementation of Python in Python. So they actually, it makes no logical sense if you describe it as something like that. It's, that basically instead of writing the interpreter in C like it's normally done, it's written in Python. And then the key to that is that it's not actually written in what I would call like full Python. It's written in a subset of Python called RPython, which is kind of this highly restricted subset of the language. And what happens is that RPython is compiled into C code. So it takes that restricted RPython, takes it down into C, and then you get sort of high performance from that, amongst other things. I mean, they're doing some other tricks. One side effect of this RPython business is that if you ever build PyPy from source, I showed a movie of it last time, but if you just do it in like a terminal, has anybody ever, I think I asked this last time, has anybody built PyPy from source before or looked at it? If you do it, this is sort of a history of what it looks like. I'll just kind of scroll through it. It goes on and on and on and on and on and on and on through just all sorts of like magic. Eventually it starts drawing like Mandelbrot sets and stuff like that. Okay, so more stuff like that. So it just fills the terminal with this stuff. And part of what I talked about last time was like what is going on with that. And I'm not going to repeat all of that, but essentially what it's doing is it's taking this version of Python written in Python and it's taking it down to C code. And that's part of where the performance is coming from. And it turns out that this RPython language is actually something that you can mess around with yourself. I mean, they use it to implement PyPy, but you can kind of mess around with it on your own, just as a sample of that. And this is the same. It's the same example that I did last time. So this is a sample of what RPython looks like. It's essentially Python. Like if you look at the code, it's like valid Python. You can actually run it as Python. So if you just set it up as like a main program, you can essentially go into a directory. Here's your here's your Fibonacci program here. You can just run that and say, hey, let's compute the 37th Fibonacci number and just run it. It'll take a while because it's pure Python, but it's just straight Python code. And the only thing that you need to do to run in this sort of restricted Python world is you just have to give it a main function. So this main function is what you have to add, and then you just have to add this other little function, target. What that target function is it just tells this RPython tool what the entry point to your program is. So it's a lot like C basically. Like if you get programmed in C or Java, you have to write a main function. It starts executing in the main function. So what you do is you just write sort of normal Python code. And then the key to this magic, if you were at the last meeting, is that there is essentially this script translate that comes with the PyPy project. So there's essentially this translation script that you have to run. And what you do is you feed it your program, and it will go off and do various forms of magic on that. So we did this last time. A number of people were sort of horrified by the output of that. So what it's doing now is it's taking that Python code, turning it directly into C code,
And we're going to end up with an executable in a second here. It takes probably about 20 seconds. Okay, so it takes about 20 seconds. You end up with this file, fib.c, essentially an executable program that got compiled there. Okay, so that's you know, that's sort of what it does, and it turns out that all of PyPy is written in that RPython subset, or that language there. Now, so a few things about that language, just as a recap. It is really first of all, the results are pretty fast. Done some benchmarks on it. You know, you'll get code that's comparable to C in terms of like its runtime performance. But the one thing about the language is like really restricted in what you can do. You can't do any dynamic typing features that you normally can do in Python. Like you can't have functions that take multiple types of arguments. You can't have lists that have multiple data types in it. So everything has to be restricted to like a single type. Same thing with like objects. So if you made a class and you started assigning attributes, it sort of looks at what the first use is, and then it sets that as a type. And if you violate that, it raises an error. So what it is it's essentially this language. It's very C-like in terms of what it does. I mean, it has restrictions on it as far as what you can do, what you can pass around as types. It actually gets compiled into C. So what I wanted to do here, this is kind of again, this is a little bit of a follow-up to the last talk. I actually wanted to go look at the C code. This is probably a really bad idea. I thought I was like, I should go look at the C code just to see what's going on. And it turns out that it's kind of horrifying and interesting at the same time. So I'm going to do the head explosion first, just to get it out of the way. This is going to be pretty mind-boggling, and it turns out that this is a really poorly documented corner of the RPython world. So there's not a lot of discussion of this. A lot of this is just like scientific experimentation, if you will. So if you mess around with this RPython thing, it turns out that it does make a bunch of C code. And you can go look at the code if you very carefully study the output of that huge Mandelbrot set thing that got made there. So if you go back to this this folder here, or the build, it will actually tell you where it's building the source there. So you can basically go to this directory, and if you do that, so let's just kind of CD in there. What you will start finding is you're going to find these like different sort of session directory. Let's go into one of these. And it turns out that this is sort of where you start to find the C code that this thing generated. So one of the things that you're going to find is there's a whole bunch of these like platform checking C files. I'm going to say more about that in a second. But what those are, they're little tiny C programs that tend to check features of the C compiler, like what different constants are, what different sizes of things are. If you were to look at one of these, like I don't know, let's just look at plat check 0. It's essentially testing something here. It looks like it's testing some values out of like the floating point library. So it's just a little bit of C code where it's testing stuff. And what those are is that you can actually just compile these things where you can say, oh, let's just compile like platcheck.c and then run it. All it does is it just runs the C compiler and prints out values of certain constants and stuff. So part of what the build process of this PyPy is doing is it's actually using the C compiler to pull information out of the environment. So that's actually part of the build process, is that. And then the rest of the code, and this is where it gets horrifying a little bit. It turns out that the rest of the code gets placed into this directory called testing1. Don't ask me why it's called that. I don't know. And what you will find is essentially just a big directory of C code. So there's a bunch of files. This is all the C code generated by this Fibonacci program. So if you were to look at that, okay, so 48 C files. What they are, I don't know. If we wanted to do like a rough word count on it, 29,000 lines of C. for that one little Python script. Now, to be fair, a lot of what's coming in here are things like the garbage collector and some other things with RPython. If you go look at the code, which you probably shouldn't, but if you want to, it turns out that all of the code gets placed into a file called implement.c, and this is where you can actually find your implement, what happened to the Fibonacci number program. This is some really nasty looking stuff. I'll sort of show you where it gets into this, but make it a little bit smaller here. Oh, it has lots of go-tos. So this is actually the sort of the translation of your main program there. There will be a quiz. There'll be a quiz on this later here. So, okay, there's the Fibonacci program. So this is sort of what happens to the Fibonacci code. Code in there is it basically turns into C. It's not the kind of C code that you would normally write. Like, what in the hell is that? Like, go to block 0, and it's like right there. Go to block 1, and it's like right there. But it's littered with go-tos. It's lots of little code fragments. Yeah, it's basically low-level assembly code. I'll sort of say more about it in a second, but that's sort of the, what the code looks like. It's basically very low level. One thing that you probably that you should know about it, though, is it is working with basically native C data types. So it's actually generating code that's like native C code. If you know anything about how CPython is implemented, or if you've ever built like a C extension to Python, it's all these like Py objects all over the place, and you have to do all this like unwrapping of values and things like that. What's going on in RPython is it's essentially generating like native C code with native data types. And because of that, it actually gets very high performance because it's not messing around with a whole bunch of custom data structures or anything like that. But the code is really, really nasty looking. And in fact, every single file pretty much in this directory looks like that. So if you were to like just pick like any one of these files, like RPython, rlist or something.c, and look at it, it's just more and more of this like block stuff. It's just essentially low-level blocks, low-level assembly code. So part of what's happening in this build process for PyPy is that it's essentially generating this very low-level C code. There are some kind of interesting files to look at. It turns out, like this implement.c that I just looked at is sort of where your functions go. There's a few other files that define data structures and other things, but you can definitely go look at it. The code is extremely low level. Where it's coming from, just so you know, is, and this is something that we did in the last talk, is we talked about how basically RPython takes your code and it turns it into these like control flow graphs. It's really almost a direct translation of these graphs into C code. So I don't know if you can see this or not, but over here, it's doing like a less than operation. You can sort of see how this thing got translated into a less than operation. So it's just sort of a rewriting of those graphs there. So that's kind of what it's doing. I mean, it's generating this very cryptic C code. Everybody want to write C code like that or mess around with it? Everyone good so far on that? Just to give you a taste of how much C code PyPy generates. So keep in mind that PyPy is this complete re-implementation of Python in Python. So I mean, it's this very big system. If you look at the build for that, I actually did it here. It consists of It actually consists of 785.c files. Okay, so when you compile the Python interpreter, it's about 785 files that come out of that. If you look at how big it is, just in doing like a simple word count, it's 9.7 million lines of code. So it generates about 9.7 million lines of C. Just to give you an idea on that, the whole C implementation of Python 3 is about 230,000 lines of C. Okay, so it's what is that, a factor of what, about 40, something like that? Yeah, 35, 40, something like that. So, so it's a lot of C code, takes a lot of time to generate that. That's why it takes it almost an hour to just compile PyPy, is that it's generated a lot of this C code. And then some other things with this. It turns out that if you want to go messing around, you can actually find out what PyPy does with your what happens with your Python code in this tool by looking at these C files. It's a little bit of a coding challenge to kind of do that, but it is something that you can experiment with. So if you wanted to, just to give you an example, if you wanted to see, for instance, what happened to like a class definition. Okay, let's just make a class. Okay, there's a very simple class definition. If I were to put that in this, I don't know why I would have this in the Fibonacci code, but just have it in there. And then if you were to maybe create one of these things, so let's just say p is equal to pair of 2, 3. I'll just print p, see what happens here. And try to compile that, you can actually sort of see what happens to that code when it gets generated. So let's actually try that real quick and just sort of see what happens with it. Lost my okay, so we're just try the translation process again, sort of see what happens. Give it another 20 seconds. Am I selling everybody on using RPython here? Fibonacci, yeah, it's really critical to do Fibonacci. Never.
That 9 million lines of code is pretty close to the size of the Linux kernel.
Is that how big the Linux kernel is? It's about 9.
It's like 13, but roughly.
Yeah, I don't think the kernel is written quite in the same way with so many go-tos, though. It's the,
I think there's one go-to in the kernel. What about if there's a comment that says dice?
yeah. Actually, one thing we could do is we could do like a grep for the word go-to on all the lines of C, and then just see how many of the 9.7 million lines are go-tos. Here, let's see what that is. So only 920,000 go-tos. So, but 10% of it is go-tos. That's yeah. Okay, so. Okay, fun time. So what I've done here is I've kind of built this again, and one of the things that you can do, and again, this is really low-level stuff. What I'm gonna do is I'm actually gonna try to figure out what happened to this pair class definition. Like, what did that turn into in C code? I mean, something must have happened to it. So what I'm gonna do is I'm gonna drop down into this temp directory. Here, it turns out that all of the structure definitions get placed into another file. So let me pull that up. Okay, so you have to kind of go searching around for it. But here's kind of the interesting thing with how this RPython works. If you kind of examine what happens to that code, you'll actually see that it turned into basically a C structure where it's just 2 longs and like a little bit of a header. What?
Why did it pick longs?
It picked longs because that's what the RPython uses to represent integers. And the reason that it picked longs is that I created a pair with 2, 3. I basically said, hey, make a pair with 2 ints. And it saw that and said, oh, that has to be a structure with 2 ints in it. And it went off and it generated C code where it's like, hey, this is a structure. It's got 2 ints in it. It has a little bit of a header on it. I think this is actually just like a little 8-byte header or something like that. But I actually find that kind of interesting as a C programmer, that it's actually able to take that Python code and turn it into something that is actually way more efficient than I would have guessed. I mean, I'm used to kind of classes in Python being very heavyweight objects. I mean, normally if you know how classes work in Python, they have dictionaries underneath the covers, and there's like all sorts of pointers and all hash tables and all this stuff. And RPython is basically going right down to C. And it's actually C code that's not unreasonable C code. I mean, it's what you would expect. So that's some of the things that you can do by messing around with this is actually just kind of experiment with it, sort of see what happens to objects, kind of look under the covers. Everybody okay with that, or still with me here? Okay. Now some other things that now where this gets really wild, and this is I don't know. We'll see how far we get with this. One thing that just boggles the mind in this PyPy project is that literally everything is written in Python. I mean, that's the whole goal of the project, right? Is to write the whole Python interpreter in Python. And there's this issue that comes up with, which is how do you access low-level libraries? There's a lot of modules in Python, like the OS module and time and math and all this stuff, that basically have to interact with C code at the C level. You know, it's like I have to call C functions, and there's this question about how does that work in this RPython environment. And one question you can ask is just how would you access C code from Python? I mean, how many people have done that? Like access, yeah, what do you use for that? C types. If you haven't used C types, by the way, it's pretty cool. I think it's pretty cool. Even though I created Swig, I can say it's pretty cool. I mean, essentially with C types, you can just say, hey, load this library, and then like here, load the math library, and you can pull out functions out of it, and then you attach like little signatures to them, and then you can call them. It's pretty cool that you can do that. Turns out that RPython basically does that. It's a slightly different interface, but there is essentially this, there's sort of this remote, or not remote, it's basically this restricted foreign function interface thing you can do in RPython, where you can essentially add this import and then just declare external functions, and they'll just show up in your RPython program. So you can actually try this out. I mean, it's actually surprisingly easy to do this. So if you were in this Fibonacci program, and for some reason you wanted to do sines and cosines from the math library manually. Okay, keep in mind there's already a math module, but I'm going to do it kind of the hard way. There's this library. You can basically say, hey, from PyPy, RPython, LL type system. Unfortunately, this is not documented very well, but you import this sort of foreign function interface module, and then what you can do is you can just say, hey, let's go grab some functions. You can say, hey, this is an external function called sine, and then you attach some type signatures to it, like that. Okay, so you just say, there's my sine function. Turns out that you're done. What? Can you, what was the question?
Do you need to map it to a library? Or?
It turns out I think the math library is already compiled in as part of RPython. So
The second argument is a list. It's a list of the argument types.
so if you had like multiple arguments, you would do that. The third argument is the return type. So if you do that, let's just try it out here. I don't know. We'll print the sign of the 20th Fibonacci number or something. I don't know why we need to do that, but you should essentially what you can do is just start calling C functions under the cover. So let's go build that real quick.
Is that any way better than C types?
What would? Oh, we're going to look at the performance of this in a second. It turns out that this is not using C types. I mean, it's its own thing under the covers. But I'll actually show you what it does under the cover. Okay, let's try that. Okay, so this thing will go off. Basically declared that external sine function, and I'll cross my fingers that it actually works here. Again, it takes about 20 seconds.
What all the curses color.
Blurring for the.
It's very important. Okay, so let's try this here. So I'll do C20. Okay, so
So now, I don't know that you can see that or not at the bottom, but there's like 2 floating point numbers showing up for, sine of 2, sine of Fibonacci. So that's actually kind of neat in a way. I mean, there is this little extra bit you have to do where you have to say, oh, I have to declare that as like an external function, and then it just like magically shows up in your RPython program as something that you can use. Now, one of the things that's also kind of interesting about that, let's go back into and look at the C code for a second. Turn off colors here. If you go into the C code and you look for that sine function, this is essentially what it looks like in the generated code. And this is a little bit cryptic, but this is actually very interesting from like just a performance point of view. Essentially, what RPython does is it makes a little function that calls the sine function with float. And you'll notice that like the data types it's using are like doubles from C. So it's saying it's passing in doubles, and then it just literally calls the C function. That's the sine function, just directly. That is way more efficient than what C-types does, or even like Swig or any of those like code generator tools. I mean, this is just like directly calling C code as if it were C code. So yeah, so you have this ability to basically call C functions with like very little overhead in that RPython tool. It's kind of amazing that works, but it does have that ability to do that. Okay, so that's another aspect of this RPython, and you actually see this a lot in like the implementation of this PyPy. Essentially, what they have to do is whenever they call external libraries, they declare the functions using this foreign interface, and then they just go and just call those. All right. Now, one comment on that. There's actually, this whole part of this RPython seems to be pretty well developed. You can do pointers, you can make arrays, you can make structures, you can do mallocs and frees, you can do memory management. It's basically all the stuff you can do in C, you can do there. And then on top of this, not to melt your head anymore, it turns out that RPython has its own C compilation configuration tool built into it. So one of the problems if you work with a lot of C code is that you have to bring in like extra libraries, extra header files, you need to declare like extra options and things like that. Turns out that this tool actually has a whole mechanism where you can declare like what header files are, what libraries are, and then on top of that, you can ask it to rip things out of the C code. You can say, hey, you know what? Like what I'm doing here is I'm saying, well, I did kind of step through it. Basically, you can say, hey, here's some library stuff that you need for the C compiler. What you're doing here is sort of setting up queries on the C compiler saying, hey, you know what? I want the value of the MPy constant. And you're basically just setting that up saying, hey, I want that. And then there's this mechanism where you can just run like a platform configure on this thing. And what that will do is run the C compiler and then fill in all these like queries that you set up. And then you can pull the values back. It turns out that this is what's driving all of that platform checking code. Essentially, you can just drop in your RPython code a whole bunch of this like C compiler config stuff, and it will just go out and find stuff out from the C compiler. It's actually kind of amazing that it does this. But if you've ever used like, I don't know if you've used like distutils or had to write like setup.py files, for dealing with like setup tools or anything like that. This is very similar to that. If you've ever used autoconf from like C, it's kind of similar to that. One very confusing aspect of this whole thing is that there's no centralized configuration anywhere. It turns out that what you do, and I'll show you some sample code in a second, is that individual modules in this RPython can just ask the C compiler to give them information. And then what ends up happening is the whole compilation part of this is scattered everywhere in the system. It becomes really difficult to kind of wrap your brain around it. So what I wanted to do is I'm just going to show you kind of a little demo of what that configuration stuff might look like. I'm almost out of time anyway. So what I'm doing here is this is this is the same Fibonacci program, but what I'm going to do is I'm actually having it interface with the C get time of day function, which is actually a relatively complicated C function. I kind of picked this on purpose, but this is it's basically a C function that takes like two C data structures, which are sort of shown in the comments here. So this is some really low-level code. And what I'm going to do is I'm actually just going to have RPython call that and just sort of show you what that looks like. Essentially what you do is you might write some configuration data in your code saying, oh, hey, okay, those are in this header file called systime. Okay, this is all C code stuff. And then what you can do is you can actually have RPython go discover stuff for you. What I'm doing here is I'm asking it, hey, go find out what you can go figure out what this struct time value thing is. So what I'm doing is I'm asking it, hey, go make a structure out of struct time val. Here are the fields that I care about. Turns out that what that will do is actually run the C compiler and like automatically discover the structure content for you. So it will actually go discover that. Here I'm asking it to build kind of a time zone structure. So what's happening is it's essentially setting up the C compiler to go discover stuff. And then down here, I run the C compiler. And then what happens after it runs the C compiler is it actually builds like data types for you that you can use. So I'm building some data types, doing this LL external thing. There'll be a quiz later, don't worry about it. I'm just kind of giving you a sample of it. And then what you can do is start writing low-level functions that basically interact with this. If you've done C programming, this little fragment here actually looks, it's a little cryptic, but it has elements of C in it. Essentially what I'm doing is I'm allocating memory. So that's what the malloc is, basically saying, hey, I want to allocate some memory. Here I'm calling the C function. Here I'm freeing memory and returning a result. And then down here, I have my Fibonacci number, and then I have it print like timing statistics around it. Turns out that what you're seeing here, this is actually what a lot of code in this RPython in PyPy tends to look like. Just kind of looking around different directories, what you'll have are sort of Python functions, like this Fibonacci, or whatever, different Python functions, but then there's this whole element of how this thing interacts with C code. And it's this bizarre, well, I don't know maybe that's a strong word, but it's kind of a mix of stuff that looks like C types, plus stuff that looks like setup.py files, where you're interacting with C compilers. And to be honest, it kind of makes my head explode. I don't know how you're feeling about it just seeing it here, but that's a lot of what's going on underneath the covers of this thing. Just giving you a little bit of a taste of sort of what it looks like. That's basically the end of the talk. It was about 40 minutes. All of the stuff that we did in this talk and the previous one is just about the implementation environment of PyPy. It's all written in this RPython. It has all these bridges to C. It's generating all this C code. We haven't even talked about how PyPy is actually implemented yet. I mean, other than it's in Python and it's in this weird flavor of it. So all of this stuff is just kind of a starting point for that. It's something that I'm still working on, still messing around with. I don't know whether I'll succeed in figuring it out, but it's a little bit formidable going into the PyPy project, trying to figure out what's going on, just as an outsider looking in. So I think with that, I'm going to stop. Any questions or concerns about any of that? So.
Besides bending our mind with the compilation of PyPy, once PyPy is compiled, it pretty much acts just like another Python interpreter, or is there anything else you know about it?
Yeah,
That's the thing. So like PyPy, if you use it, it should just work like normal Python. You can run all your normal Python scripts on it.
Is there any advantage of compiling your Python scripts with RPython into PyPy with it, or is there any opportunity with that? What are the reasons?
It should be able to do, I mean, one of the things it has like a just-in-time compiler. So if you have like Python code that needs to run faster, it should just run faster. I think my main motivation for looking at this is I want to know to what extent people can tinker with PyPy. because I think one of the things with CPython is that a big success of Python is that people have been able to mess around with it, kind of at all levels. You know, you can go into the C version of Python, you know, like the C interpreter, and look at it and say, oh, I want to tweak this. I'm sort of curious whether that's possible in PyPy, because it, you know, maybe it's just me, but PyPy to me feels like a very magical project that is almost impenetrable to know how it works or how to get involved with it, other than just like you download it and you run it. You know, it's like.
How many hours have you spent reversing it so far?
I've been working on it kind of off and on.
For most of probably the last month or so.
So that's the answer to the question of whether or not you can temper
it is kind of an experiment. I think
The PyPy guys are a little bit annoyed with me because they're like, why don't you ask these questions on IRC? And I'm like, no. I was like, part of what I'm doing is kind of like an experiment to see whether I can actually get a grip on PyPy by just downloading it and looking at it. And just using like web pages, like using their documentation and using the source code. Can you make any sense out of the project at all? And it's proving to be rather challenging. I mean, it's at all levels. Part of it, I think, part of the challenge. So let me back. Have you ever wondered, like, this is just like a rhetorical question or a hypothetical question. Have you ever had the thought, wouldn't it be cool if everything was written in Python? I've had that thought, right? You know, it's like, oh, Python is great. It would be cool if everything was written in Python. Having looked at PyPy, I'm not so sure. Because you're in the PyPy project, and it's like, RPython is written in Python, and PyPy is written in Python, and like the config tool is written in Python, and all these things are written in Python, and they all use like cross libraries with each other. Like this library is used by RPython, but it's also used by PyPy, and this other library uses this library as well. I can't decide whether looking at this project is like the movie Conception, or what is that? Yeah, Inception, or the movie or Black Swan. Has anybody seen like Black Swan, where she goes like insane and like kills herself at the end of the movie? Or, I didn't mean to spoil it or anything, but it's like you know, you look at this thing and it's just like mirrors and Python everywhere you look, and it's really, really hard to get a handle on what belongs to what. Like, does this piece of Python belong to the PyPy piece, or is it this part of the RPython piece? One of the things with CPython is if you're looking at C code, you know what that is. Like, it's like if it's C code, it's part of the implementation of CPython. If it's Python code, you run it on CPython. And so it is really challenging. So, I don't know.
Ironic, because I thought part of the reason for PyPy to exist was that they wanted a Python interpreter which was written in Python so that they could modify it in Python. I thought that was part of their idea was to make it more maintainable.
I know.
That's the claim. Maybe it's true. I mean, it's just, the question is at what level. I mean, it may just be one of these things where there's just such a steep learning curve to get to like a certain level of enlightenment. It's like you sort of maybe it's one of these things where you'll reach like a certain point. It's just like, oh, I see the light, and then, oh yeah, it's totally trivial. But getting into it just as a newcomer is pretty. I don't know. It's pretty hard.
And I'm a little bit scared because I wouldn't consider myself just to be like a newcomer off the street. I've done a lot of C programming, a lot of Python code. If I'm struggling heavily with it, I can only imagine.
What version of C does it output? Is it like C99 or something else?
I'm pretty sure it's ANSI. Just ANSI C.
Can you go back to the pair example? Can you use objects polymorphically, or do you get a compile time error?
Oh, you get a compiled error if you use anything like that. It will work
if the objects if they all inherit from each other. But if you had if you had a class where like sometimes an attribute was a string and sometimes it was an int, it would crash on that.
What happens if you have a method attached?
Pardon?
What happens if you have a method attached? Like, it was a struct. It came out to be a struct. What happens to that method?
Oh, if there's a method on there, I think it generates code very similar to C++, where it's like there's like a V table and it does like function pointers and things like that.
So in a world of parallel programming and Scrum and all these methodologies. By looking through this, do you have any notion of what methodology those who wrote PyPy? I mean, is this just a total organic process? Is this a waterfall process? What process did they use to come up with this project?
This is purely from just reading about the project. I know they're very heavily into test-driven development, and a lot of the coding seems to be done in sprints. The code is really hard to figure out.
I'm trying to let me let's just go in there for a second. I mean, if you're kind of curious about it, I mean, if you go into the PyPy project, so I mean, this is sort of what you get if you download the source of the thing. Let me pull the window up a little bit here. If I can get to the Windows resize here. So if you go into the project, I mean, this is sort of what you're presented with. It's just that. I don't, you know, if there's a README, it's okay. There's a little bit of getting started. That's the extent of the README, is the one page there. But most of the code is in this PyPy directory, and then you know, a lot of subdirectories for different pieces: annotation, JIT, interpreter, module, object space, RPython. If you look at the code for it, and I think this is really kind of a lot of the challenge with it, is that it's not really documented at all. I mean, one of the things, this is actually probably the part that I find most mind-boggling myself, is that most of the files in PyPy look something like that at the start, where it's maybe a dozen to 20 imports, highly nested from all sorts of different places in the project. You know, tools, object spaces, annotation. It's really hard to know how all those pieces kind of fit together. So you have lots of imports, and then a lot of the code you don't see a lot of comments in there. It's like not a lot of comments, not a lot of doc strings. And then you look at that, and it's you know, and then you see sort of non-standard Python usage of things like, what's that? Okay, some meta programming trick. So it's really hard to kind of just to kind of look through that and make sense of it. A lot of what I've been doing is more I would say sort of experimental kinds of like more of a scientific experimental approach on PyPy, where it's like, oh well, I'll try this experiment and then I'll either go look at the generated code and just see what happens. The other thing that I've done quite a bit is inserting like breakpoints into this. Like I'll just look at something and I'm like, oh, I wonder how this gets. Like how do you even get here?
How do you insert a breakpoint?
PDB. So you might just insert like a breakpoint with PDB, and then you'll just like run the translation process, and you'll just hit the breakpoint, and then you're just like, oh, let's look around and see where we got. How did we get here?
Can you set breakpoints in the generated the C code or the actual final product?
You probably could, but I don't know how helpful it would be. Yeah, one of the things that I often do with like breakpoints, I mean, I can kind of give you an example of that. If you wanted to set a breakpoint, I don't know whether you know this about PDB, but one thing that I actually find useful about PDB is that you can just manually, if you do PDB set trace, it will just manually put a breakpoint on something. So oftentimes I'll just insert like a breakpoint somewhere, and then I'll just go to another terminal and I'll just say, okay, let's just run the translation process and see what happens. Now I don't know what's going to happen here. I mean, it might be code that doesn't run at all. Okay, so we'll just let it go, and then we'll just see whether, okay, so we hit a breakpoint. Now the question is, where the hell are we? So, I mean, you can do a where on it, and you can say, well, how did I get here? And then, it's simple, yeah. I mean, I mean, you do have to be a little bit scientific with it. I mean, in the sense that usually there's some kind of goal where it's like, oh, I'm very focused on like, well, how do lists get processed, and like, where does this happen, and so forth. So I mean, you can mess around with it, but it is really, it's really challenging to kind of get a handle on it.
So how maintainable is this project?
As long as
I
people
wish
keep
I would-
paying the
Yeah,
developers,
keep paying the
keep funding the
developers. Yeah.
existing developers, and they don't go anywhere else. Very maintainable.
It's kind of amazing. I mean, that it does
What it does. I mean, RPython is actually a really amazing piece of work. If you think about what it's doing, all the C compiling, all the optimizations and things that it's doing, it's not documented very well at all. I think one of my interests in it is that, again, this sort of tinkering factor. I'd kind of like to try and document some of this stuff. It might be a crazy idea, but there's sort of a need for documenting like what's going on in this RPython. So I sort of see that as maybe like a possible sort of side project, trying to, basically doing lots of science experiments with RPython and then trying to write that up and saying, hey, here's what I found out about this RPython.
Would it be helpful to even put in code documentation? Because I don't think so. I think you'd always have to be at a higher level to talk about it as if it's your doctoral thesis or something.
Yeah,
I don't know. I mean, I think honestly they don't really intend for people to go looking around at this stuff, but there's a side of me though, it's like, I think people, like if they want maintainers on the project or they want people to contribute bugs or patches or stuff, it has to be something, there has to be some level of like ability to hack on it, so.
what?
You said contribute bugs.
Contribute bugs, yeah.
Contribute bugs.
No, I mean, I think about
About it like, well, I mean, it's just like a selfish thing, like that stuff I did with the global interpreter lock. The only reason I was able to do that is I was able to understand Python C code. I mean, it was basically C code. And it's like, I look at the Python interpreter and it's like, oh, it's C. You could identify like, oh, here's where the global interpreter lock is. There's like a specific file. You could search for it. You could go in there and mess around with it. I don't know on this yet. I have not reached a comfort level with it to even know how to tackle a problem like that. I mean, it's sort of, there's so many interlocking pieces that.
Did you see a report post from yesterday called Fast Enough VMs in Fast Enough Time?
yeah,
I saw that. There was like the guy talking about RPython and.
He's the only person outside the team who's written a substantial chunk of RPython.
yeah, he'd written how many lines of RPython? He'd written his own VM for another language. I forget the name of the
Yeah.
language, but
Yeah, the idea was to get a jig
yeah.
VM for it.
Yeah, I saw that. If you read that article, he also complains about the lack of documentation or the sort of impenetrable nature of some of the RPython stuff. But I don't know. So any more questions on that? I think I'll probably listen to see everybody getting hands in here.
Does it seem like translate.py is doing 80% of the same work every time?
Yes.
Okay.
Yeah, that's an interesting open question because it's like
So one of the things with this translate tool is it's essentially doing whole program analysis. Like it actually takes the entire Python interpreter and sucks it up into memory and does like whole program analysis on that. I sort of wonder like how much of that code is replicated or how much of it could be cached.
Right.
Because
one of the issues that
Your
they
C
have.
library hasn't changed in the last 5
Yeah,
years.
yeah. And also, like, if you were working on this, like, if you were to make, like, a single line change in the Python code, and then you wanted to actually rebuild the full performance version of PyPy, you actually have to retranslate the whole thing. It takes, like, an hour. So, that's kind of an interesting question. It's like, how much of that work could be replicated? I've kind of had this idle thought floating around where...
I wonder if somebody could hook up maybe something like Redis or something on the back end of the translator. It's like one of these like NoSQL databases. We're just like we'll set up a huge machine with like a bunch of memory, and then have the translate tool like populate that database. Could you actually speed it up by looking in the database for stuff that has a change? Do you do? I mean, maybe you could do like signatures on it, like what?
Oh, tests?
It's probably quite cool.
Oh yeah, there's a whole
test suite for that. I haven't really messed around with that so much because I actually haven't gotten to a point of actually writing PyPy code, but as opposed to just trying to understand what's going on. So.
All right. Well, I think that's it. At some point, I may be back talking more about it if I can wrap my head around it. It's crazy, but we'll see what happens. So, also, there's
Probably going to be something at PyCon related to this if I can put it together. So maybe you'll see me there. So. All right. I'll let everybody go.
that's it.